Hey, everybody. It's Wednesday, February 24th. And as you can see here in the aim today, our goal for today's video is all about how we can use concepts associated with conservation of momentum to analyze experimental data. Now, as is always the case when we are wrapping up a unit, we now get to the experimental design part of that unit. And I think it's really important for us to spend some time talking about conservation of momentum experiments because, number one, conservation of momentum experiments are good experiments in general because they sort of combine the skills that we've worked on and discussed for the whole year. Number two, because they can be combined really seamlessly with conservation of energy ideas. And so they can sort of do like a 2-for-1 on an experimental design question. And number three, they haven't asked one in a while. And that's on a practice exam or on a real test. They asked a conservation of energy experimental design a few years ago, but a straight up conservation of momentum, like a collision experimental design question, hasn't been asked, I think, since the first practice test. So there is definitely an opportunity for us to really try to prepare for this test by focusing on this question, because it really wouldn't surprise me if this was the question. Now that they've cut out the last 3 units in the course, conservation of momentum and conservation of energy are the big picture topics here. Obviously, Newton's laws of motion as well, but since Newton's laws of motion inform conservation of momentum, I really think focusing on energy conservation and momentum conservation here makes a lot of sense, because you're going to see this all over the free response section of the exam. Now, similar to how we did it yesterday, I attached worksheets to the Google Classroom post, and I want you to do those worksheets following along with the video, just like you did yesterday. But for today, what I want to do first, before we get to the worksheets, is I want to just do a little background discussion. Essentially, what we're doing here is we're kind of revisiting an experiment that we've already done earlier in the year, but in kind of a different way. If you remember from earlier this year, we discussed how to design an experiment to measure the mass of an object that was part of a tabletop Atwood's machine. If you remember, we talked about how we can use motion data for an Atwood's machine to figure out the mass of one of the objects if we measure all the other stuff. And what I hope you learned is that the principal equation that governs the system is the key to performing the experiment, because it tells you exactly A, what to measure, and B, how to analyze the data to determine the quantity you're trying to measure experimentally. So in other words, you take the equation, you solve it for the thing you're looking for, and that's what you need to measure. And so hopefully the idea is, if you know the basics about how to get all the equations for the situations, and you know the devices you're supposed to measure that equipment with, then this part of the test should be fairly straightforward. Let's just take a moment to remind you of what we did at the beginning of the year. If you remember, in the beginning of the year, we did an experiment to measure the mass of the hanging object in an Atwood's machine, a tabletop Atwood's machine. And so we said, if you want to determine the mass of object 2, well, you take the equation for the acceleration of the system and you solve it for m2. If you solve that equation for m2, what we saw that you got was you got m1a divided by g minus a. And now the whole point of this discussion that we're having right here is this equation is all you need to design the experiment, because you should know that the mass of an object is going to be measured with a scale or a triple beam balance. And you should know that the acceleration is going to be measured, and notice that's here and here, with a motion sensor. And so really, if you just take a look at the equation, and you, of course, remember that there are any constants in there that you're just going to use the number for, the variables in the equation that are not constants are the variables you need to measure. And if you know how to measure those things, if you know you can use a motion sensor to measure acceleration, or if you know you can use a scale or a triple beam balance to measure the mass of an object, then you're in business. What's particularly nice about these equations, I think it's important to remember also, is that when you get them in the form of a fraction, answering the follow-up question on the AP test, which is like always going to be, now that you've measured M1A, and you, of course, know G, so you can calculate M2, how do you calculate M2? Now, you could say, well, I'm going to use this equation 400,000 times for all my different trials, and then I'm going to average them all together, but that's kind of silly. What's really the best thing to do is to produce a graph where the slope is equal to what you're looking for, which in this case would be M2. And so what we said is because the slope equation is delta y over delta x, whatever is on the y-axis should be whatever's the numerator of that equation, so that would be M1a, and whatever should be graphed on the x-axis is what's going to be in the denominator of that equation. And so if you graph M1a on the y-axis and g minus a on the x-axis, you're going to get a bunch of data points that lie along a line of best fit, and the slope of that line of best fit is going to be, in this case, the mass of the object you're trying to measure. And that's the idea behind experimental design questions. And so what I want to do, the reason why I'm saying we're revisiting this experiment, is because now I want to take a look at another experimental design situation where we'll be measuring the mass of an object. So the question here is, how can we design an experiment to measure the mass of an object, which we'll call M2, just for consistency with the last diagram, involved in a perfectly inelastic collision? So, because this is a perfectly inelastic collision here, remember, we're saying these objects are sticking together. And so really your task here, what I want you to think about here in a moment, is what will we need to measure and with which pieces of equipment, and what will we need to graph in order to produce a graph with a slope equal to the mass of the object we're calling M2. Instead of using an Atwood's machine to determine the mass of this object, we're going to be using a perfectly inelastic collision. Now, I want you to pause this video here and think about it. Play around with the equation, think about what you need to measure, think about what you need to measure those quantities with, which equipment you need to measure it with. And then when you hit play, we're going to go over it. Before you hit pause, though, I want to give you one little hint or one little piece of advice, which is to keep it simple and make your life easier. As is always the case, but particularly for these kind of experiments, there is a hard way to do this experiment, and there's an easy way to do this kind of experiment. And I want you to realize that in general, for experiments, keeping it simple is your best bet. Take a couple minutes to pause this video here and play around with the equation for a perfectly inelastic collision and think about what you need to measure and what you need to graph and what tools you need to make those measurements to measure the mass of the object we're going to go ahead and call M2. And when you hit play, we'll go over the answer. In order to determine the mass of this object we're going to call M2, because we are dealing with this object in a situation that we refer to as a perfectly inelastic collision, we're going to need to use the equation for conservation of momentum for a perfectly inelastic collision. And so that's M1v1 plus M2v2 equals the sum of the masses times v prime. Of course, the right-hand side of the equation looks the way it does because the objects are stuck together. They basically function as one unit with the same final velocity. And so what you need to realize is that in order to solve this equation for M2, we have to distribute the v prime to the M2 and M1 to make this equation workable. So the first thing I'm going to do with this equation is I'm just going to distribute the v prime to both terms. So now I have M1v1 plus M2v2 equals M1v prime plus M2v prime. Now there are a lot of ways that you can perform this experiment, but I hope you internalized what I was saying about keeping it simple. There are a lot of variations to this experiment you can make. You can make both of the objects go toward each other and have a head-on collision. If they're going to stick together, you got a lot of options. You can make them go toward each other, crash into each other, and have a head-on collision. You can make them follow one another and have like a rear-end collision where this object behind is going faster. But those are not the simplest scenarios. The simplest scenario is where you take your object and you just have it crashed into by the other object. This object could just be sitting there at rest. And so keeping this situation as simple as possible means setting the initial velocity of our mystery mass equal to 0. Now, I want to be clear because some people have usually asked me this in the past. Yes, we could set m2 equal to 0, but some kids usually ask, well, why wouldn't we just set the other object with an initial velocity of 0? Why is it the mystery mass that we want to keep with a velocity of 0? It's a perfectly good question. Notice in this particular equation, we have an m2 appearing in two locations. And so just strictly from a mathematical standpoint, if we're going to solve this equation for m2, we would have to gather both m2 terms on the same side of the equation and then factor out the m2. It's not that big of a deal, but it's important to realize it makes the equation significantly simpler if we just get rid of the other term that has an m2 in it, because now notice the only m2 term in this equation is right here. And that makes solving for m2 a heck of a lot easier. In general, and if you remember, when we were talking about an experimental design question where we were trying to find the acceleration of an object in an inclined plane, we said, like, yeah, you can start the object from some non-zero initial velocity, and then you'll have to use a device to measure the initial velocity of the object. But why would you? You can just have the thing start from rest, because whether it starts from rest or not doesn't really affect its acceleration down a ramp. It's the same thing here. Whether you have this object start from rest, it doesn't affect the mass of the object. So keep it simple. When you go through now that it's easy because you only have one term with an m2, and you solve this equation for m2, you get m2 equals m1 times v1 minus v prime divided by v prime. And that is an equation for an experimental design question that you should love to see. Why should we love to see that? Well, number one, there are only two different types of quantities in that equation, mass and velocity. And number two, it's a fraction, which means it's really super friendly to graphs. So first, let's talk about the equipment. Notice here, you're going to have to measure M1. And of course, M1, you're going to measure with a digital scale or a triple beam balance. And V1 and V prime, you have options. You can use a motion sensor. You can use meter sticks and stopwatches. But the best device that you can use to measure the velocity of a lab cart is going to be a photogate. You are eventually going to see a video of me doing this experiment. But when we do this experiment in class, there are actually little tiny poles that screw into the top of our lab carts. And when we attach those little posts to the lab carts really just end up looking like this. The post is what passes through the photogate. And basically, all we have to put into the computer is the width, or really the diameter, of the post, and the photogate is able to measure the velocity of the cart. It makes this experiment really nice and pretty straightforward. And so while on the AP test, if you just say, I'm going to measure the velocity with a motion sensor, that works. But the photogate, in my view, is the best way to do it. It's particularly good because you won't get interference. If you're taking a motion sensor at the end of a track with two carts on it, trying to measure velocities consistently is going to be kind of annoying. However, if you have photogates positioned, putting one here to measure the velocity of M1, and then after it crashes and sticks to M2, which we usually do with like these little Velcro tabs that attach to these carts. Other carts that we actually use in our class have magnets too, so we can make them stick together. We put a post on M2, and then just another photogate past that. So M1 goes, it passes through photogate number 1. This photogate measures V1. And then the carts stick together, and it goes through photogate number 2, and this photogate measures V prime. And that's it. It's a very simple setup. What's additionally nice about this experiment, as I said with this equation here, is that because it's a fraction, we can use our simple setup to produce a very simple graph. If we plot V prime on the x-axis, because that's in the denominator of the equation, and we plot M1 times V1 minus V prime on the y-axis, then we're going to get a graph with a slope equal to M2. That's a pretty nice experiment. Like I said, I really do think this is going to be an important experiment for the AP test. So I'd like you to take a moment to pause this video here and summarize what we just said here in your notes. A drawing of the experimental setup over here on the right side would be a smart thing to do. And when you hit play, we'll move on to the worksheet. Okay, so let's move on to the worksheet here. If you open up the attachment for today's post here, you'll see a worksheet with the title Conservation of Momentum Experimental Data Analysis. And as it says here at the top, earlier in class, like just 2 minutes ago, we developed a procedure for an experiment that would allow us to determine the mass of a laboratory cart by way of a one-dimensional collision. Our experiment featured an inelastic collision in which cart A of a known mass was set in motion toward cart B, which was initially at rest, and made use of photo gates to measure the velocity of cart A before the collision and the velocity of the combined carts after the collision. It says, suppose a group of students carried out the experiment. The data they collected is displayed in the graph below. Now, these kids, for whatever reason, decided to, because it's a graph of position versus time, they decided to use a motion sensor. And so you can see here, their graph of position versus time is displayed on the top of that worksheet. And so I think it's important whenever you see a graph on the AP test, especially when it looks a little scary and complicated like this one, is to just take a breath and get a lay of the land. They give us a key. So you can see here over in the key on this side of the page, we've got cart A with its velocity, or excuse me, with its position measurements indicated by these large dots. Cart B represented by these small dots over here. And then notice what's very important to realize is you see the black dot for cart B inside of the circle for cart A. That's how we know the carts are stuck together. Because after the time of the collision, which is at 1 second, these carts are always in the same position. Now, it's also important to realize, whether you've realized it or not, that these data perfectly represent what we were just talking about in our simulated experiment. Notice here, the cart, which is being called cart B here, we called that M2 before, same difference, is at a position of 1.5 meters for the first second. That means it's not moving. On the other hand, cart A is moving. Then they get stuck and they move on together. The first part of this question says, given the mass of cart A, which is going to be 1.5 kilograms, we'll use that for our M1 in the equation we were just talking about before this, use the graph to calculate the mass of cart B. Explicitly indicate the principles used in your calculation. Now, whenever you see explicitly indicate the principles used in your calculation, really what they're talking about is like, what physics concept, what physics principle are you applying to the problem? It should be pretty clear to everybody that since this is a perfectly inelastic collision, the principle that we're using here is conservation of momentum. And so what I'd like you to think about first, before you do that, is how are you going to get the data you need to calculate the mass? Let's just go back to that mass equation real fast here. How are you going to get the data you need to calculate the mass, according to that equation, from this graph? I want you to take a second to pause this video here and think about it. And when you hit play, we'll talk about it. Okay, what I hope you realized is that since this is a position versus time graph, you need to find the slope to determine the velocity of these objects, because the velocities are in the equation. And so what you need to do here, printing this out as key, you need to draw a line of best fit. Now, that's an okay line of best fit. Obviously, drawing this on the computer is a little harder than drawing it by hand. But the key to drawing the line of best fit, you should remember, is that you want to, as best you can, draw as many dots above and below the line. The same number of dots above the line should be below the line. So notice here, this one's basically exactly on the line. I've got 2 above and 2 below. That's good. Here, I've got these 2 basically on the line, but we can call this one above, 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 above. It's not great. I want you to take a stab yourself at drawing a line of best fit and then calculating the slope of those lines of best fit. Once you have that done, I want you to unpause the video and we'll discuss the answers. Okay, now to go over the answers to this question here, I don't want to use the lines of best fit that I just drew because it's hard to draw them on the computer. I actually scanned a copy of lines of best fit that I drew by hand and added them to the slide here. So notice there are a couple of things that should be realized. A line of best fit is something you are drawing by hand. Because we're not getting a computer to do it, there's room for error. And so there's some wiggle room here. Basically, in the scoring guide to this question, it just says like the student uses their brain to draw a line of best fit that doesn't look totally ridiculous. I think it actually uses the word reasonable. What you definitely want to pay attention to, though, when you're looking at your line of best fit, what you definitely want to pay attention to is where your line of best fit crosses the grid spaces perfectly. Like if the line of best fit goes here, or like let's just say, for example, this spot right here, I have no idea what the y coordinate of that line is. But if it was right here or right here, I would know exactly what the y coordinate is for that point on the line. And so my points here, and let me just do this in red so you'll be able to see them. My points here that I used for this calculation was this point and this point. For my first velocity, notice these are going to be used to calculate v1. And then for the second line, I used this point and this point to calculate v prime. And so the first thing that you need to do for this question, which, yeah, is a little involved, is calculate those slopes. Now, we're not going to go so nuts about showing the work for the slopes, but let's just do it very quickly here. We'll say here first, for V1, I'll go back to black for this. For V1, we're going to use y2 minus y1 over x2 minus x1 to calculate our velocity. And if you look at my line, this is at 1.4 meters, and this is at 0.5 meters. So I'm going to write 1.4 meters minus 0.5 meters. And then I'm going to divide that by the times for those coordinates, which would be 0.9 seconds minus 0.3 seconds. And when you do that math, 1.4 minus 0.5, that's 0.9. 0.9 minus 0.3 is 0.6, and 0.9 over 0.6 is 1.5 meters per second. And so my V1 for this experiment I have written down as 1.5 meters per second. Cool. For V prime, I need to do the exact same thing. Now, let's be clear before we move on to the calculation for V prime. If you didn't get 1.5, but you got something close to 1.5, that's fine. I think the answer scoring guide for this question shows the answer as 1.6. But just as long as you use a line of best fit that doesn't look totally ridiculous, they're going to give you credit for this. Now, if you look here, I have my first, or let's go to the second one first because it's 2 minus 1. This dot here is at 2.1 meters per second, and this, or excuse me, 2.1 meters, and this coordinate is 1.6 meters, so I've got 2.1 minus 1.6, my numerator, and then I just have to use the time coordinates for those points. 2.1 meters occurs at 1.9 seconds, and then 1.6 meters occurs at 1.1 second. So in my denominator here, I'm going to have 1.9 seconds minus 1.1 seconds. And so here, I got 2.1 minus 1.6, which is a half, and then that's going to be divided by 1.9 minus 1.1, that's 0.8. Notice this one's going to be smaller, that's good. 0.5 divided by 0.8 is 0.625 meters per second. And so my V prime is 0.625 meters per second. Now, first of all, just right off the bat, that's good. The reason why that's good is because it should be smaller. The objects have crashed. Some of the initial kinetic energy present in the system was converted to thermal energy. We would expect the carts to move slower at the end. Cart 1 transferred some of its momentum to cart 2, and so it gets slowed down as a result. So now that we have both velocities, we're in business to calculate everything we need to calculate here. You can use MA like they gave you in the problem. It doesn't really matter. But now we know M1 or MA is 1.50 kilograms. V1 is 1.5 meters per second, v prime is 0.625 meters per second, and we are looking here for m2. Take a second to pause this video here and calculate the mass of this second cart, and when you hit play, we'll move on. So the equation we derived before for the mass of this second cart, m2, is m1 times v1 minus v prime over v prime. And so when you plug that in here, you get m1, 1.5 kilograms, times v1, 1.5 meters per second, minus v prime, which is 0.625 meters per second. And then we're going to divide that by v prime, which is 0.625 meters per second. And there you have it. When you do that math, at least with my numbers, so I should say when I do that math, I get 2.1 kilograms. If you got something reasonably close to that, it is going to be accepted on the AP test. I'm sure some of you might have even gotten 1.5 meters per second, or 1.5 kilograms. And that's fine, because just as long as you take a reasonable approach to finding the lines of best fit, it's going to be accepted for this question. And that's it for part 1. Moving on to part 2 of this worksheet here. Part 2 of this worksheet asks an interesting question. It says the students are now asked to consider the kinetic energy changes in an elastic collision, specifically whether the initial values of the physical quantities affect the fraction of the mechanical energy dissipated in the collision. How could you modify the experiment to investigate this question? Be sure to describe the calculations you would use, but do not actually do any algebra. I think this question is kind of scary. I know the first time I saw this, I was like, oh my gosh, this is going to be so difficult to teach. I've already told you everything you need to know to be able to answer this question. The equation is the key to the experiment. They are asking you whether the initial values of any of the physical quantities affect the fraction of the mechanical energy. What are the initial values? The initial values are m1 and v1. So what they're asking you is how will changing m1 or v1 affect the fraction of the lost kinetic energy, essentially. So what I want you to do here is think about the equation that we developed. Perhaps you should go back in your notes if you forgot it, and look at the equation for the fraction of the kinetic energy lost in the collision. Look at the variables that are in that equation, and then answer the question, how would you need to modify the experiment? It says, be sure to describe the calculations you would use, but do not do any algebra. Like I said, this is not a particularly easy question. However, you should know enough to be able to at least come up with a response that would earn you the majority of the points. Take a second to pause this video here and think about the answer to this question. When you hit play, we'll talk about a possible answer. As we mentioned before we started even talking about this experiment, the key to these experiments are the equations. Look at the equation for the fraction of energy dissipated in a collision. It's the initial energy minus the final energy over the initial energy. If you expand out the equation, I hope you will see what I mean. The initial kinetic energy present in the system is going to be just the kinetic energy of object 1. That's 1/2 m1 v1 squared. The final kinetic energy is going to be 1/2 m1 plus m2 times v prime squared. And the final, or excuse me, not the final, the initial, again, is just going to go in the bottom, 1/2 m1 v1 squared. Look at that equation. Which of these quantities is our experiment already set up to measure? Is our experiment already set up to measure m1? Yeah. What about v1? Yeah. What about v prime? Yeah. What about m2? Yeah, that was the whole point of the experiment. The point here is, for this experiment, there doesn't need to be any change to the experimental apparatus whatsoever. Every single thing that we're doing is already perfectly set up to answer this question. And so a sample response can look like this. We can determine whether the initial speed of the moving cart affects the energy dissipated in the collision. The only other possible answer, at least as far as this part is concerned, is saying we can determine whether the mass of m1 affects the energy dissipated in the collision. The rest of this, it really is just thinking about a controlled experiment. You keep M2 the same every time. You keep V2 the same every time. If you're, like I put here, changing the initial speed V1, then you're going to keep M1 constant. If you're going to change M1, then you're going to keep V1 constant. The only thing you're going to vary is the thing you're going to vary, and that's it. You want to determine the effect of changing that quantity and that quantity alone on the fraction of the kinetic energy lost in the collision. So I wrote here, we can determine the initial speed of the moving cart. We can determine whether the initial speed of the moving cart affects the energy dissipated in the collision. Using the exact same setup we have, we can vary the initial velocity of the moving cart and measure it along with the final velocity of the two-cart system. We can calculate the initial energy using the equation 1/2 m1 v1 squared, and the final kinetic energy using the equation 1/2 m1 plus m2 v prime squared. Then we can use the equation k fraction equals k naught minus k final over k initial to see if the fraction of the kinetic energy changes when the initial speed of the object changes. It's important to realize, despite the fact that these things sound complicated, they're really not. Basically, they're asking you to describe the procedure for a controlled experiment. You guys have been doing this forever. I'm sure you talked about in living environment, like you could take the one plant and give it the exact same food and put it in a dark closet, and take another plant and give it the exact same food, but put it in the light outside, and all other factors being the same, you can see how the growth is different, or like whatever. That's the point here. If we keep everything else the same besides the speed V1, then we can truly tell how V1 affects the fraction of the kinetic energy lost in the collision. Take a second to pause this video here and write that down. This is confusing, I think. If you have any questions, please feel free to ask about it. Take a second to pause here, and when you hit play, we'll move on. Okay, now I think some of this might be easier to understand if we actually just take a look at some data. Whenever I do an experiment with you guys in class, which unfortunately you're missing out on this year, I always test it out myself before I have you guys do it. So I want to show you some of my data. In this experiment, I used just the empty lab cart. Our empty lab carts are 0.799 kilograms, 799 grams. And so that's just the mass I use for every single trial. Now, it's basically impossible to throw the cart at the same speed, but you want to throw the cart at different speeds initially so you can get your different data points, right? That's the whole point here. We want to use different initial speeds because the initial speed of cart 1 has no effect on the mass of cart 2. The only thing it's going to change is V1 and V prime, and so that will give us a nice spread of data. With a photo gate, I measured all the different individual V1s. You can see that here. The lowest speed I threw it at looks to be 0.79 meters per second. The fastest speed I threw it at was 1.11 meters per second. Of course, my V primes vary in accordance to that. My lowest V prime looks to be 0.57. Notice that should make sense. If I got a low V1, then I have a low V prime. My highest V prime looks to be 0.8. Notice that makes sense because that resulted from my highest V1. And so, as we mentioned, if you want to produce a graph that has a slope equal to the mass of the object, you have to graph M1 times V1 minus V prime on the y-axis and V prime on the x-axis. And so I've used Excel, notice I've got a little formula in there, to calculate all these things for me. Pretty cool. Then I graphed. And when I made my graph here, notice I don't have the axes labeled because I was just doing this quickly for myself. All of my data points fell pretty clearly along a line of best fit. That line of best fit has a slope equal to 0.3013 kilograms, or about 301 grams. And if you look at my data, if I actually calculated M2 individually for each trial, it would look like this. Notice it's all around 0.3 kilograms. The actual mass I had was 298 grams. So the slope of my line was about 301 grams. So notice that's pretty close. That gives me approximately an average experimental error in measuring this mass of less than 2%. And that's pretty cool because that's like a nice little efficient experiment that you can do, which gives you the mass of this cart pretty easily here. Now, of course, the real reason I wanted to show you this data was for the energy part that we just answered. Notice they really asked you to design this experiment without considering the answer. It's an interesting question, though. Does the initial speed of cart 1 affect the energy dissipated in the collision? It might. Like, why would it make sense that it would? Well, if the cart's going faster, it's going to have more kinetic energy. So there's going to be like a bigger crash involved with the collision. Might that deform the cars more and end up making the thing lose more energy? I don't know. Of course, the obvious answer to the question is there's only one way to find out. Let's do an experiment. And as we mentioned, all the data that we were initially measuring was enough to be able to perform the experiment. So as you can see, I could use all of the information I already had to calculate the initial kinetic energy in the system. Notice the equation I used is just 1/2 m1 v1 squared. I could also use all that data to calculate the final kinetic energy. Notice it's just 1/2 m1 plus m2. Notice my m2 data is all here. M2 actual is 0.298 times d2 squared. And notice d2 here is v1 prime. And so I've got 1/2 m1 plus m2 times v prime. And there's all my final kinetic energies. I can then use that information to calculate the lost kinetic energy. Notice this is just the difference, according to that formula, L2 minus K2, between these two values. I just took that minus that. That's my lost energy. Piece of cake. Then I could use that to determine the percentage of the kinetic energy lost. And what I noticed, because I never knew the answer to this question before I did this experiment, what I noticed was kind of weird. It's always basically 27%. Now, I know fraction is not the same thing as a percent, but everybody should realize if you just take the fraction and you multiply it by 100, then that's it. So notice here, in my equation, I took the absolute value of the lost kinetic energy. So basically, instead of taking K initial minus K final, I took K final minus K initial and then just took the absolute value of it. And then I divided it by the initial kinetic energy. And then the only difference is I just multiplied it by 100. And I got always an answer of about 27%. Weird. So that means the fraction is always about 0.276-ish. And that's kind of weird. Why the heck would I always get the same fraction of energy lost in the collision? Let's look at that equation. Now, I know this video is already getting kind of long, but I hope you bear with me on this because I think this is pretty cool. Let's get an equation for the lost kinetic energy in a collision that is really kind of expanded out. Now, what did we just see from conservation of momentum is a good question for us to ask. And what momentum conservation just showed us here is that if we have m1 v1, that's the initial momentum in the system, plus is equal to m1 plus m2 times v prime, we can solve this equation for v prime. Notice I've already gotten rid of the m2 v2 term because we started that object at rest. And so what the conservation of momentum equation tells us is that v prime, which we measured in this experiment, but just to solve for it algebraically, is m1 v1 over the sum of the masses. We're going to need that later. Okay. Now, conservation of kinetic energy is not a requirement here. So we have lost kinetic energy. The fraction of lost kinetic energy, which we just saw was basically always the same, is the initial kinetic energy minus the final kinetic energy over the initial kinetic energy. Let's expand that out. If we expand that out, we get 1/2 m1 v1 squared. Notice that was the initial kinetic energy, 1/2 m1 v1 squared. The final kinetic energy is 1/2 times the sum of the masses m1 plus m2, because they're stuck together at the end, times v prime squared. Basically, we treat them as one unit, moving at the same final speed, v prime. And then we, of course, divide that by the initial kinetic energy, which is just 1/2 m1 v1 squared. And so now, this doesn't really give us anything to work with until we take the result from conservation of momentum and substitute it in for v prime. And so when we do that, we get a bit of a mess. The fraction of the kinetic energy here is 1/2 m1 v1 squared minus 1/2 m1 plus m2. And then now we've got to take our v prime, which is m1 v1 over m1 plus m2, and we've got to square it. As I mentioned here, we get a mess. Of course, before we even square it, we've got to, of course, not forget about the denominator here, which is 1/2 m1 v1 squared. I'm going to go ahead and write the result of this equation, the result of the squaring, on the next line. So in my fraction of kinetic energy equation, I'm just going to keep around the initial kinetic energy 1/2 m1 v1 squared. Then I had 1/2 times m1 plus m2. And then notice here what I subbed in was m1 v1 over m1 plus m2, and I have to square the whole thing. That's going to give me an m1 squared v1 squared on the top, and then I've got to square this sum. So I have in the numerator m1 squared v1 squared over, and I'm just going to keep this as m1 plus m2 squared. Now I could multiply that out, like FOIL it, if you will, distribute, but there's no need for that, because if you notice, and let me just write the denominator here so I don't forget it, 1/2 m1 v1 squared. If you notice, I've got an m1 plus m2 right here, and I got an m1 plus m2 right here. So basically, that m1 plus m2 cancels one of these m1 plus m2s nice and easily. And so what I'm left over with then is I'm left over with 1/2 m1 v1 squared minus 1/2 m1 squared v1 squared over m1 plus m2. And then all of that is over 1/2 m1 v1 squared. Now I want to clean this up a little bit. And the way I'm going to clean this up a little bit is I'm going to write 1/2 m1 v1 squared. This numerator is almost 1/2 m1 v1 squared. Notice the only difference is it's got an extra m1. It's multiplied by an extra m1. So if I factor out 1/2 m1 v1 squared, the only thing I'll need to multiply 1/2 m1 v1 squared by to get 1/2 m1 squared v1 squared is just an m1. So that's going to remain behind in the numerator. Notice if I take 1/2 m1 v1 squared times m1, then I get this, 1/2 m1 squared v1 squared. And then, of course, in the denominator, I'm going to have m1 plus m2. And then in the denominator of the whole thing, I'm going to have 1/2 m1 v1 squared. And now here's the cool part. I got a half, and a half in every term. Cancels. I got an m1 in every term. Cancels. I got a v1 squared in every term, so it cancels. I got a 1/2 m1 v1 squared in every term, so it cancels. And so what I'm left over with then, after all of those cancellations, is 1 minus this, m1 over m1 plus m2. This equation is kind of gross because I have 1 minus this fraction. And it's important to realize we can simplify this pretty easily. Notice the denominator here is m1 plus m2. So in order to make this 1, I'm just going to put m1 plus m2 in the top. m1 plus m2 divided by m1 plus m2 is 1, right? And so I can rewrite this equation pretty simply as m1 plus m2 over m1 plus m2, that's 1, minus m1 over m1 plus m2. And what that gives me, remember, when you add fractions, you keep the denominator. I have m1 plus m2 minus m1. And this positive m1 cancels this negative m1. And that leaves me, for my fraction of kinetic energy, m2 over m1 plus m2. What the heck? What that equation says is the fraction of energy lost in a collision is equal to the mass of that second stationary object and how that mass compares to the total mass in the system. It has nothing to do with the initial velocity of the objects. Now, that's kind of weird. But of course, we can test that. Before we do that, I think this is a valuable derivation to have in your notes. So take a second to pause this video here and write that down. And when you hit play, we'll go ahead and test that. Okay, so let's go ahead and test that. Notice we've already seen something that probably makes sense. Because when we varied the initial speed of cart 1, we just saw in my data the fraction of the kinetic energy that was lost didn't really change. It was always about 0.27. What we just said, though, is that that's always equal to the ratio of m2 over the sum of the masses. What if we actually take m2 over the sum of the masses? Oh my God, it's 0.27. And that's the idea here. Notice in this experiment, what I got is on average, my lost kinetic energy fraction differed from that fraction by about 2%. And that's well within the range of experimental error. Why didn't it work out to be that fraction exactly? Well, there's a lot of good reasons. The cart jumped the track a couple of times. Not all of the kinetic energy lost was able to be detected because it turned into like sound and other weird forms of energy. And so this result is well within the range of experimental error. And that means that the equation we just derived is supported by experimental evidence. The fraction of kinetic energy lost in the collision only has to do with the masses and not with the velocity of an object. Specifically, it's how the mass of the stationary object compares to the sum of both of the masses. And that is pretty cool. And notice this 2.9-ish percent difference was really contributed to pretty greatly by these two trials here, this one and this one. And as you can see, in the original mass determination, these were my most error-prone trials as well. And so that probably tells you there was something a little iffy with those trials. But either way, it's a very good result. All right, now let's just wrap up this worksheet because this has already been quite long. A question you should be fairly familiar with if you've been paying attention this year. Number 3 says there will be sources of error in the measurements taken in the experiment, both before and after the collision. For your procedure, will the uncertainty in the calculated value of the mass of cart B be affected more by the error in the measurements taken before the collision or by those taken after the collision, or will it be equally affected by both sets of measurements? Justify your answer. We've actually talked about this before. Uncertainty in a measurement. I want you to take a second to pause this video and take a stab at this answer here. And when you think you've got an answer and an explanation, hit play and we'll go over it. All right, the answer here is pretty straightforward. After the collision is our answer. Due to the fact that we are only measuring velocities, the uncertainty arrives in the velocity measurement. Since we'll measure the velocities using identical photo gates or motion sensors, the error, or the uncertainty, will be the same before and after. However, because the cart is moving slower in part 2, or after the collision, the uncertainty in the measurement, which for a photo gate or motion sensor is usually about 0.2 meters per second, the uncertainty in the measurement will be a much larger percentage of the final speed. As a result, the mass of cart B is affected more by the uncertainty after the collision. Remember, we've been talking about this since the beginning of the year. Smaller measurements are affected by uncertainty more. And so because the final velocity, or the velocity after the collision, is smaller, that velocity is affected more by uncertainty. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, last note for today, very quick, big note here. The uncertainty in any measurement will always affect a smaller measurement more, since the uncertainty, which will be the same for both measurements, will make up a larger percentage of the smaller measurement. The reason why I taught this in late September, early October is for these kind of experiments right here. Because notice on that worksheet, they asked that on the AP test. If you remember that, it's an easy question. And with that, that's it for today. All right, everybody, have a good one.